In a constellation called Hercules, 1100 light-years from where you sit, a planet exists that should be impossible. It is more than twice the width of Jupiter, yet its material is lighter than a marshmallow. A comet-like tail of helium streams behind it. Its star is dying, swelling, getting ready to swallow it whole. Tonight we travel to puffy giants that defy physics, dayside winds hotter than melted iron, and a world running out of time. If this kind of journey calms your mind, hit subscribe. Now close your eyes. We begin. The year was 2008. A small telescope in Arizona, smaller than a kitchen table, was watching a faint star in the constellation Hercules. The star itself was unremarkable, a pale point of light, one of millions catalogued in dusty databases. Nobody expected anything from it. Then the light began to flicker. It dropped, just slightly, every 4 days and 19 hours. A tiny dip, less than 2%. The kind of flicker that could be a passing cloud, a faulty sensor, a smudge on a lens. Astronomers almost dismissed it. Almost. The dip was too regular, too clean, too deliberate. Something was passing in front of that star. Something circling it. Something blocking its light over and over with mechanical precision. The team running the survey, a small network of automated cameras called the Hungarian Automated Telescope, started looking closer. They expected to find a small companion, maybe a hot Neptune, maybe a brown dwarf. What they found was nothing they had prepared for. Whatever was passing in front of this star was enormous, wider than any planet ever confirmed, wider even than some of the smallest stars known to science. And yet, when they tried to measure its mass, the readings came back tiny, almost laughably small. Picture an empty water balloon stretched across an entire town. Imagine something the size of a mountain that weighs less than a dinner plate. That was the contradiction sitting in their data, a gigantic, world-sized object that barely had any substance to it. Scientists call this kind of object a puffy planet. The name sounds gentle, almost cute. The reality is anything but. These worlds shouldn't really exist according to standard physics. They are inflated to impossible volumes by furious heat. They leak gas into space like a slow bleeding wound. They live on borrowed time. The signal from this particular star was so strange that the discovery sat in limbo for years. The host star was rotating extremely fast, smearing its light across the spectrum, making mass measurements nearly impossible. From 2009 to 2012, astronomers kept trying and kept failing. The numbers refused to settle. The planet refused to confirm. For 4 years, this object existed in scientific purgatory, real enough to see, too strange to verify, too massive in size, too small in weight, too quiet in spectrum. Some scientists privately wondered if the data was wrong. Maybe the star had a partner. Maybe the planet was an illusion in the math. Then, in 2016, a technique called Doppler tomography finally pinned it down. The shadow of the planet was traced as it crossed the star's surface, frame by frame, like a fly walking across a flashlight. The mystery object was real, and it had a name, HAT-P 67b, a bland scientific label for what would soon become the largest single planet ever confirmed by humanity. A world so enormous, so contradictory, so doomed that it would force scientists to question how planets are even allowed to form. But the size of this world was only the first surprise, because the star it orbits, the engine of its destruction, is hiding something even stranger. A secret written into its dying light, a secret that explains why this giant exists at all. The star at the center of this story is called HAT-P 67. It sits about 1100 light-years away from Earth, in a quiet corner of Hercules. To human eyes, even through a backyard telescope, it would look like nothing special, a faint white dot among thousands of others. But this star is not nothing special. This star is in trouble. HAT-P 67 is what astronomers call an F-type subgiant, slightly hotter than our Sun, slightly larger, slightly older, and in stellar terms, it is in the middle of a quiet catastrophe. It has finished burning the hydrogen in its core. The fuel that kept it stable for billions of years is nearly gone. The star is starting to swell. Imagine a person aging in fast forward. Imagine the body slowly thickening, the skin growing redder, the heart starting to slow. That is what is happening to this star, but on a cosmic scale. Over the next few 100 million years, HAT P67 will balloon outward. Its surface will cool. Its color will deepen. It will become a red giant, one of the universe's most violent and bloated stages of stellar life. For most planets, this would be a slow tragedy in the distance, a drama unfolding across vast space. But HAT P67b is not most planets. It orbits its star at less than 1/10 the distance between Earth and our Sunday. It is essentially hugging the surface. When this star expands, it will not just heat the planet, it will swallow it. Astronomers calculate that within 150 to 500 million years, HAT P67b will be completely engulfed. The star's outer layers will reach out, wrap around the planet, and absorb it. The planet's atmosphere will be stripped first. Then, the core, if it has one, will sink into the star's churning interior. The planet will simply cease to exist as a separate object. There is also a second, hidden character in this story. The host star has a faint companion, a red dwarf, much smaller, drifting at a distance of 3,400 astronomical units. That is roughly 3,400 times the distance from Earth to our Sunday. This tiny partner is so far away that it plays almost no role in the planet's daily life, but it watches, a silent witness to the slow death waiting to happen. The dying star is also rotating extremely fast. It spins so quickly that its light is smeared and stretched, which is why the planet was so hard to confirm. A young, calm star would have been easy to read. This one is essentially screaming. Here is the strangest part. The planet's orbit lines up almost perfectly with the star's equator, tilted by only about 2 degrees. That is unusually neat. Most hot Jupiters arrive at their stars through chaotic gravitational shoves, ending up tilted, sideways, or even backwards. This one drifted in gently, through the disk of gas and dust that originally surrounded the young star. A peaceful arrival, a violent ending, a planet that traveled gently into its own grave. But this gentle migration created a much bigger puzzle, because when astronomers measured how wide the planet actually is, the number that came back broke their models, broke them badly. Try to picture Jupiter, the largest planet in our solar system, so massive that every other planet, including Earth, could fit inside it more than 1,000 times. A swirling ball of hydrogen and helium, 88,000 miles wide, banded with cinnamon-colored storms and a great red spot bigger than our entire planet. Now double it. That is HAT P67b, roughly 180,000 miles across, wider than the gap between Earth and the Moon, twice over. If you placed it in our solar system where Jupiter sits, it would dominate the sky of every world out to Saturn. It would not just be a bright dot, it would be a visible disk, big enough to see its bands and storms with the naked eye, even from 1 billion miles away. This is the largest planet ever confirmed by humanity. Other candidates exist. Some objects out there might be wider, but they are tangled in scientific debate. They might be brown dwarfs, those failed stars that hover in the grey zone between planet and sun. They might have radii so uncertain that the error bars cover half the data. HAT P67b is different. Its size has been measured cleanly, repeatedly, and confidently. 2.14 times the radius of Jupiter, give or take a tiny margin. Let that scale settle for a second. If you scaled Earth down to the size of a marble, Jupiter would be a basketball. HAT P67b would be a beach ball. Now imagine that beach ball spinning 4 days from one face of its star to the other. Imagine it streaming gas behind it like a comet, Imagine it bloated, glowing, and rapidly losing mass. Volume is where the comparison gets truly absurd. Volume scales with the cube of the radius. A planet twice as wide is not twice as big. It is roughly 8 times the volume. So inside hat P67b, you could fit about 8 Jupiters. Inside it, you could fit more than 10,000 Earths. Stack them, tile them, drown them in its atmosphere. They would barely take up space. Here is the punchline that breaks the brain. This planet is more than twice as wide as Jupiter. It contains roughly 8 times Jupiter's volume, and yet it has less than half of Jupiter's mass. Less than half. Some early measurements even suggested less than 1/3. Imagine a freight truck that weighs less than a car. Imagine a skyscraper that weighs less than the foundation of a single house. That is the kind of contradiction we are looking at. Standard physics says this should be impossible. Gas giants have a maximum size. They cannot keep growing indefinitely because gravity becomes self-defeating. Add more material to a gas giant, and at some point, it just compresses, getting denser instead of bigger. Most large planets sit near a natural ceiling, somewhere around 1 Jupiter radius. Hat P67b is twice that ceiling. It is roughly where the universe says nothing should be. So, how is this thing holding itself together? What is keeping it inflated? What kind of strange physics turns a Saturn-mass planet into something twice the width of the largest world in our solar system? The answer involves heat, distance, and a structural secret hiding in the planet's atmosphere. A secret that, once you understand it, reveals just how fragile this giant really is. Pick up a marshmallow. Feel its weight in your hand. Almost nothing, right? Soft, fluffy, a little airy. You can squeeze it between 2 fingers and barely notice the resistance. That fluffiness comes from how it is built, mostly air, a thin lattice of sugar holding pockets of nothing. A marshmallow has a density of about 0.5 grams per cubic centimeter, half the density of water, soft and forgiving. Hat P67b has a density of about 0.06 grams per cubic centimeter, roughly 1/10 that of a marshmallow. Less than balsa wood, less than cork, less than the styrofoam in a takeout container. If you could somehow drop a chunk of this planet into a swimming pool, it would not just float, it would bob up and ride the surface like an inflatable beach toy. Density is the secret door into how a planet is built. It tells you whether you are looking at a ball of rock, a sphere of water, or a fluffy cloud held together by gravity. Earth has a density of about 5.5 grams per cubic centimeter, dense and rocky. Jupiter sits at about 1.3, already pretty puffy. Saturn, the famous lightweight, comes in at about 0.7, low enough that the entire planet could theoretically float in a giant ocean. Hat P67b laughs at all of these numbers. Its density is so low that scientists have started using food comparisons in research papers. Marshmallows, cotton candy, whipped cream. These are not casual jokes. They are the only honest way to describe what this planet feels like. Structurally, here is what is happening inside. The planet is mostly hydrogen and helium, the 2 lightest elements in the universe. These gases are normally compressed into a tight ball by gravity. In Jupiter, they form a deep, swirling, pressurized atmosphere with crushing pressures at the bottom. In Hat P67b, the same gases are heated so violently and persistently that they refuse to settle. They expand. They fluff up. They puff outward like dough rising in an oven that never turns off. The heat comes from the host star, just 6.5 million miles away. The planet is bombarded with so much radiation that its atmosphere is constantly inflated. Imagine baking a soufflé and never letting it cool. The structure stays inflated as long as the heat keeps pouring in. Take the heat away, and the whole thing would collapse. This is why puffy planets are so rare. Most of them lose their atmospheres quickly, within 100 million years or so, because the same heat that puffs them up also strips them away. Hat P67b somehow held on for over 1 billion years. That is the mystery scientists are still chasing. Standing on the surface, if there were a surface, would feel surreal. The atmosphere would be so thin and stretched that gravity would barely tug at you. The horizon would curve gently into a hazy, glowing blur. The line between planet and space would be soft. There would be no clear top, no clear bottom, just layer after layer of warm, fluffy gas, getting thinner and hotter as you climbed. But the planet is not just thin, it is hemorrhaging. Every second, tons of its atmosphere are escaping, bleeding into space, forming a strange tail behind it. A tale astronomers have only recently begun to truly understand, and what they found there is haunting. On Earth, a year takes 365 days. Long enough for seasons to cycle, long enough for snow to fall, for forests to bloom, for the Earth to lap its star one full time around an orbit of 93 million miles. On HAT P67b, a year lasts 4 days and 19 hours. Read that again. A complete revolution around the star. A full birthday cycle. Faster than a long weekend. The planet hurtles around its sun at speeds that would make any human imagination strain. Roughly 100 miles per second. That is over 360,000 miles per hour. At that speed, you could fly from New York to Tokyo in less than 7 seconds. The orbit is so tight that the planet is almost grazing the surface of its star. It sits at about 0.065 astronomical units. An astronomical unit is the distance from Earth to the Sunday. So this planet is sitting at less than 7% of that distance. Closer to its star than Mercury is to ours. Closer than any planet has any business being. To picture it, imagine our Sunday now. Imagine a giant balloon planet, twice the width of Jupiter, orbiting just a few solar diameters above the Sun's surface, skimming through the outer atmosphere, roasting from every angle. That is the daily reality of HAT P67b. Such a tight orbit changes everything about the planet's experience of time and space. A day there is meaningless in the human sense, because the planet is tidally locked. One side faces the star permanently, the other side faces eternal night. There is no sunrise, no sunset, no noon, just a permanent day side, blasted by stellar fire, and a permanent night side, frozen in a glow of redirected heat. The temperature contrast between the two sides drives some of the most violent winds known anywhere in the galaxy. Atmospheric jets race from the day side to the night side, redistributing heat at supersonic speeds. Picture a wind so fast it would tear the wings off any aircraft Earth has ever built. Then picture it howling continuously for billions of years. That is the everyday weather of this world. A year of 4 days also means tidal forces are extreme. The planet feels its star's gravity pull harder on its near side than its far side. This stretches the entire planet into a slightly egg-like shape. Imagine a basketball gripped between two hands, squeezed gently but constantly, never released. That stretching is part of what slowly tears at the planet, part of what is going to kill it. In human terms, the absurdity is hard to grasp. A child born on this planet would celebrate their first birthday before their parents finished planning the party. A school week would last longer than the planet's year. A pregnancy on Earth, 9 months, would be over 600 years on this world. Civilizations there, if they could possibly exist, would be measured in tens of thousands of orbits per generation. Time itself feels broken on HAT P67b. The pace of everything is sped up. The light show, the gravitational pull, the heating, the cooling, all of it cycles faster than humans are wired to imagine. But the speed is only one piece of the story. Because at this distance, at this proximity, the heat reaching the planet's atmosphere is not just intense, it is destructive. And the next number, the temperature itself, will sound less like a planet and more like a furnace at the heart of a star. Mercury, in our solar system, is the inner sentinel, the smallest planet, baked by our sun, scarred with craters, roasted on one side and frozen on the other. It orbits at about 36 million miles from the Sunday, close enough that during the day, its surface reaches 800 degrees Fahrenheit, hot enough to melt lead. HAT P67b sits about 6.5 million miles from its star. That is roughly 1/5 the distance between Mercury and the Sunday. 1/5. Imagine taking Mercury and shoving it 5 times closer. Now imagine its host star is bigger and brighter than our own, roughly 1.5 times the size of the Sun, and significantly more luminous because it has aged into a subgiant, glowing harder as it dies. The geometry is almost cartoonish. From the planet, the star would not look like a small bright dot in the sky. It would dominate everything. It would fill nearly half the visible sky with a wall of fire, climb to the day side of HAT P67b, and there would be no clear horizon. There would just be the star, a glowing curtain wrapped around half of existence. This is what closeness means at planetary scale. The host star is no longer a sun, it is a sky. The light is no longer warming, it is consuming. Standing on the day side, every direction you looked would be glowing the same white-hot color. Every breath, if you could breathe, would be drawn from gas hot enough to melt rock. There is another consequence to being this close. The star's gravity is gripping the planet with terrifying force. The pull is so strong that the upper atmosphere of HAT P67b is being slowly peeled away. Hydrogen and helium atoms in the highest layers are gaining enough energy from stellar radiation to escape the planet's gravity. They get pulled outward. They get streamed away. Astronomers have a name for the threshold where this becomes serious. They call it the Roche limit. Beyond that limit, a star's gravity overwhelms the planet's ability to hold itself together. HAT P67b is close enough to be flirting with that boundary. Some calculations suggest that as the host star continues to swell, the planet will eventually cross the line entirely. When that happens, gas will not just leak from the top of the atmosphere. The planet will start to come apart in ribbons. Picture pulling cotton candy off a paper cone. The bulk of it stays in your hand, but the wisps trail behind, curling into the air. That is what may be happening to HAT 67b, slowly at first, then faster, then catastrophically. Near the end, the planet's tight orbit also means there is no escape from the heat. There is no cool season, no relief on the far side from a thick atmosphere. The heat is constant, relentless, billions of years of non-stop solar bombardment. The planet has been simmering in this furnace for over 1 billion years, and astronomers are still asking how it has survived this long without losing its atmosphere completely. That survival is part of what makes this planet so scientifically valuable. It is a stress test for everything we thought we knew about gas giants. It is a planet that should have been stripped bare by now, and yet it stands, bloated, glowing, bleeding, defiant. But the heat itself, the actual surface temperature, is even more extreme than the sky implies, and it pushes this world into territory that starts to overlap with the lower edges of certain stars. Iron melts at about 2800 degrees Fahrenheit. Pour molten iron into a mold, and it glows orange-white, hot enough to set wood on fire from across a room, hot enough to ignite the air itself if conditions are right. To stand near it is to feel the heat pressing against your skin like a wall. The atmosphere of HAT P67b is hotter than that. The planet's equilibrium temperature, the heat baked into it by its constant exposure to its star, is roughly 1900 Kelvin. In Fahrenheit, that translates to about 3000 degrees. Hot enough to vaporize most metals, hot enough to glow a deep sullen orange in the dark. If you somehow placed an iron cube on the day side of HAT P67b, it would not just melt, it would boil away into vapor, then into individual atoms drifting in the wind. 3000 degrees Fahrenheit is not just hot, it is structural failure hot. It is the temperature at which most familiar materials simply stop being themselves. Glass would flow like water. Aluminum would have evaporated long before. Even tungsten, the hardest metal humans use to build the filaments of old-fashioned light bulbs, would start to soften and creep at this kind of heat. The atmosphere itself, though, is mostly hydrogen and helium, two of the most stable, lightweight gases in the universe. They do not melt or boil in a normal sense. They simply expand, they get faster. The atoms zip around at higher and higher speeds, bouncing off each other, pushing outward, refusing to be packed in tightly. This is the engine that keeps HAT-P67b inflated. The heat is not just a side effect of being close to the star. It is the structural backbone of the planet. Without it, the atmosphere would slump and condense. With it, the planet stays bloated to twice the width of Jupiter, defying every classical model of gas giant evolution. But the heat does more than puff the planet, it sorts it. The day side, which always faces the star, is hotter than the night side, which always faces away. The temperature gap drives massive winds. Some models suggest dayside to nightside winds blowing at thousands of miles per hour. Imagine a hurricane that never weakens, never spins down, never loses its eye. Now, imagine that storm wrapping around an entire planet, from blazing day to glowing twilight, day after day, year after year. The colors of the planet, if you could see them up close, would be strange. Hot Jupiters this temperature often glow with their own light, a deep red or even purple, like an ember held in invisible tongs. The day side would shine brightest. The night side would still glow faintly, because heat from the day side spills over the terminator and warms the dark side too. There would be no nighttime in any earthly sense, just degrees of fire. This level of heat is also why this planet's atmosphere is bleeding into space. The hottest atoms in the upper atmosphere reach speeds high enough to escape the planet's gravity. They drift away, they pile up behind the planet. They form a tail. That tail, when astronomers finally caught a clear look at it, told a story so unsettling that it changed how scientists think about how planets like this die. Every now and then, science finds something that breaks its own rules. A creature that lives where nothing should live. A material with properties that classical equations forbid. A planet that, by every conventional standard, should not be there at all. HAT-P67b is one of those things. Standard models of gas giant evolution paint a clean picture. A young gas giant forms in a cold disk of dust around a new star. It is born small and dense. As it ages, it cools, contracts, and stabilizes. By the time it reaches 1 billion years old, it should have settled into a roughly Jupiter-sized world, maybe a little smaller, maybe a little bigger, but always inside a predictable range. Heat can change this picture. A gas giant placed close to its star gets puffed up. It stays larger than it would in cold space, but the puffing has limits. There is a soft ceiling around 1.5 Jupiter radii where most hot Jupiters max out. HAT-P67b sits well above that ceiling. It is not just slightly bigger than expected, it is in a category of its own, 2.14 Jupiter radii, roughly 40% larger than the soft ceiling. And the underlying mass is so low that the planet has the density of a foam sponge. The numbers do not match anything theorists have prepared for. The combination of size, mass, and age, all at once, breaks the usual evolutionary tracks. There is another oddity. Planets with this density are expected to lose their atmospheres in less than 100 million years. The thinking is simple. A puffy, hot, low-gravity planet leaks gas into space rapidly. It cannot hold itself together for long. It deflates, loses mass, and either becomes a tiny core surrounded by nothing, or gets stripped to almost nothing by its star. HAT-P67b has stayed bloated for more than 1 billion years. That is at least 10 times longer than the simplest models predict. The planet has somehow kept its atmosphere intact, while every standard equation said it should be gone by now. Something is keeping it inflated. Something is replenishing what it loses. Something is breaking the rules. One leading idea involves the host star itself. The star recently entered its subgiant phase, brightening and swelling in a hurry. Some scientists think the planet was small and cool just a couple 100 million years ago, and only recently got pumped up by the rising radiation. In other words, this puffy giant may be a temporary phase, a snapshot of a planet caught in the middle of being inflated, like a balloon at the moment of stretching. If that is true, then this world is doomed in two ways. First, by the heat it is now experiencing, which will eventually bake away its atmosphere. Second, by the swelling star itself, which will eventually swallow it whole. There is also a humbling thought hidden in all of this. Every time astronomers find a planet that breaks the rules, it forces a quiet revision of our understanding of the universe. The rules are not really rules. They are guesses based on the planets we have already studied. Worlds like HAT P67b remind us that the cosmos has imagined more strangeness than we have. And the strangeness has just begun, because behind this defiant giant, scientists have tracked something even harder to explain. A glowing structure in space, larger than the planet itself, drifting in a slow, ghostly dance. Comets have tails. Everyone knows that. As a comet approaches the sun, ice and dust boil off its surface, streaming behind it in a glowing stripe that can stretch for millions of miles. It is one of the most iconic images in astronomy. A small, icy body with a sweeping ribbon of light behind it. Now imagine a comet's tail attached to a planet twice the width of Jupiter. That is what astronomers have found at HAT P67b. A long, ghostly tail of helium streaming away from the planet as it orbits its star. Not a faint wisp, a massive, observable, scientifically measurable structure, so big that when scientists try to estimate its effective size, the number reaches roughly 6 times the radius of Jupiter. The planet itself is 2 Jupiters wide. The tail of escaping atmosphere stretches 3 times that. Helium is hard to detect at first glance. It is invisible to most simple observations. But when starlight passes through the helium-rich gas, trailing the planet, it leaves a fingerprint, a specific absorption signal at a particular wavelength of infrared light. By watching how starlight changes as the planet transits, astronomers can map where the helium is. They can measure how much is there. They can trace its shape. What they found surprised them. The tail did not stretch only behind the planet. It also stretched ahead of it, a leading tail, reaching out in front of the planet's orbital direction, brighter, larger, more dramatic than the trailing tail. This is unusual. Most cometary tails point only away from the source of the radiation. They are pushed back by stellar wind and pressure. A leading tail is something different. It is a sign that the planet is losing material from a part of its atmosphere, where the gas, instead of being pushed back, is escaping in a direction that lets it run ahead of the planet on its orbital path. The most likely explanation is that the planet is shedding material primarily from the day side, the hottest, most irradiated face, the side that is constantly in the line of fire. Astronomers using the Hobby Eberly telescope in Texas, paired with an instrument called the Habitable Zone Planet Finder, were the first to see the leading tail clearly. The trailing tail was dimmer, harder to confirm, but also present. 2 streams of escaping gas, sweeping out from the planet in opposite directions, like ribbons fluttering off a balloon in flight. The scale of the structure is hard to overstate. If you could see it with the naked eye from a nearby vantage point, the planet would not look like a sphere. It would look like a hazy, glowing comma, a glowing center with luminous arms reaching out into space. A planet caught in the act of dissolving. Each second, this tail represents a slow loss. Tons of helium and hydrogen drift away, day after day, year after year, million-year stretch after million-year stretch. The planet is donating its atmosphere to space, atom by atom. The tail is also a window. By studying how it moves, how it glows, and how it interacts with the host star's wind, scientists can learn about the upper atmosphere of HAT P67b in detail. The escaping gas carries information about the planet's chemistry, temperature, and structure, information that would be impossible to get any other way. What this tale reveals about the rate of loss is the most chilling part of the story, because the numbers do not just describe a dying planet. They suggest a planet that has only recently begun to die. A planet does not just lose its atmosphere all at once. It bleeds, atom by atom, particle by particle, gas slipping away into the surrounding vacuum. Earth is doing it right now, in tiny amounts. Hydrogen escapes from the upper atmosphere of every world with sunlight. Even Mars, with its thin shell of carbon dioxide, is losing gas to space every second of every day. HAT-P67b is bleeding so fast that astronomers can almost watch it happen. The estimates vary depending on the model, but the general picture is staggering. The planet is losing thousands of tons of gas every second. Some studies suggest the upper end could reach hundreds of millions of metric tons per Earth day. Imagine an object the size of a small mountain detaching from the planet every 24 hours and floating away into space. Then another, and another, for millions of years. This is not the gentle leak that most planets experience. This is a hemorrhage. The reason is the same combination of factors that makes the planet so strange in the first place. Low gravity, extreme heat, intense stellar radiation. The atoms in the upper atmosphere are constantly being kicked into high-energy states by the star's ultraviolet light. At the same time, the planet's gravity is too weak to fully hold them. They drift up, gain energy, and escape. Helium is one of the easier atoms to track because it lights up at a specific wavelength when illuminated by starlight. But helium is not the only thing escaping. Hydrogen is leaving too, in even larger quantities. Hydrogen is the lightest element in the universe, and on a planet this hot and this puffy, it is the first to flee. Some studies have looked at the absorption signatures around the planet during transit and inferred the presence of an extended cloud of hot gas surrounding the planet on all sides. A planet wrapped in a glowing fog of its own escaping breath. Behind the planet, the cloud trails into a tail. Ahead of the planet, it streams into a leading tail. To the sides, it expands like a slowly inflating bubble. Where does it all go? Most of the gas is eventually swept away by the stellar wind, the constant flow of charged particles streaming out from the host star. Some of it is captured by the star itself, falling inward and being absorbed back into the stellar atmosphere. Some of it escapes into the wider system, drifting outward into interstellar space. There is a haunting circular logic to this. The planet's host star is bigger and brighter because it is aging, and it is aging because over billions of years it has been steadily processing its own fuel. The star's increased radiation is now stripping its planet. The stripped material, in part, is flowing back to the star. The dying star is reclaiming the gas it gave to its own planet long ago. Another insight is more practical. The rate of loss is so high that the planet cannot keep this up forever. Its atmosphere is finite. Even at modest assumed loss rates, the entire envelope of hydrogen and helium will be gone in less than 1 billion years. Combined with the predicted engulfment by the swelling star within 150 to 500 million years. This gives the planet 2 countdown clocks. Either the atmosphere goes first, or the star eats the planet first. Either way, HAT-P67b does not have long, and the way astronomers measured this slow death is one of the most elegant scientific stories in modern astronomy. In a quiet stretch of southwest Texas, on a high mountain ridge called Mount Falks, sits a strange and beautiful instrument called the Hobby-Eberly telescope. It does not look like a normal observatory. The mirror at its heart is segmented, made of dozens of hexagonal pieces fitted together like a honeycomb. The telescope itself is partially fixed in place, designed to swing only along a limited path while letting the Earth's rotation carry the sky across its view. It looks, from the outside, like a giant geometric eye half buried in the desert. This telescope, paired with an instrument called the Habitable Zone Planet Finder, became one of the key witnesses to the strange life of HAT-P67b. The instrument is designed for a delicate task. It splits incoming starlight into thousands of slivers of color, looking for tiny fingerprints left by gases between Earth and the star. When a planet transits across its host star, light from the star passes through the planet's atmosphere on its way to us. Anything that absorbs at specific wavelengths leaves a mark. Helium leaves an especially clean mark in a part of the infrared spectrum where Earth's own atmosphere is thankfully quiet enough to see through. A team led by astronomer Michael Gully Santiago used this setup to perform a multi-year campaign on HAT P67b. They watched transit after transit. They watched moments before transit. They watched moments after. They built a long, careful library of starlight slices, looking for the helium signal. What they saw was not a faint blip. It was a strong, persistent absorption pattern. The helium signal lasted long after the planet should have finished its transit. That meant gas was still blocking starlight after the planet itself had moved on. Something invisible to the eye, but real to the instrument, was trailing behind the planet across the face of the star. The opposite was also true. The helium signal began before the planet's edge crossed the star. That meant gas was reaching ahead of the planet, blocking starlight before the planet itself arrived. A leading tail, exactly where physics did not always predict one to be. By comparing the strength of the leading and trailing signals, the team could tell which side of the planet was losing more gas. The leading tail was bigger, the trailing tail was smaller. This was the smoking gun for preferential dayside mass loss. The planet was leaking the most from the side that always faced the star, because that side was being baked the hardest. The Hobby-Eberle observations did something else important. They confirmed that the mass loss was not a brief event. It was a continuous, ongoing process, visible across years of observation. Scientists had previously seen hints of escaping atmospheres on hot Jupiters, but here, finally, was a clear, repeatable, multi-tail signal at one of the largest planets ever found. The discovery turned HAT P67b into a kind of laboratory, a stress test for theories of atmospheric escape, a natural experiment in how gas giants die. The data has been cited in dozens of papers. The follow-up observations are ongoing. Hubble Space Telescope time is being aimed at the planet too. Future observations from the James Webb Space Telescope are expected to reveal even more about what kinds of molecules are sneaking out into space. But the Texas telescope was only the beginning, because the very shape of the tail and which side leaked harder contained another clue. A clue about the structure of the planet itself. Picture a person standing in front of a roaring fireplace. Their front side gets warm fast. Heat presses against their face, their chest, their hands. Their back, in the cooler room behind them, stays comfortable. If the fire roars hot enough, the front of their clothes could even start to scorch, while the back stays untouched. Now, imagine a planet locked in that exact pose, forever. One side facing the fire, one side hidden in shadow. No rotation to spread the heat, no relief. That is the reality of tidal locking on HAT P67b. The planet always shows the same face to its star. The day side is permanent. The night side is permanent. There is no gentle temperature smoothing across a normal day-night cycle. Just two utterly different worlds welded together along a single shimmering line called the terminator. Because the day side takes the full punishment of stellar radiation, it is hotter than the night side. The atmosphere there is more inflated, more stirred up, more energetic. Gas atoms on that side are bouncing around at speeds high enough to reach escape velocity. They drift up, push past the gravitational boundary, and float free into space. The night side, being cooler, has slower atoms. They stay closer to home. The result is exactly what astronomers measured with the Hobby-Eberle observations. The day side leaks faster, the night side leaks slower. Most of the escaping gas trails away from the day side, which, because of the planet's orbital motion, ends up forming a tail that runs ahead of the planet rather than directly behind it. There is a subtle piece of physics in this geometry. As the planet moves forward in its orbit, gas escaping from the dayside has, on average, a slightly different velocity than gas escaping from the nightside. The leading tail is fed mostly by dayside losses. The trailing tail is fed by nightside losses. Both exist, but the dayside is so dominant that the leading tail is much brighter, larger, and more visible. This pattern would not be possible without the tidal lock. On a planet like Earth, where the rotation spreads heat out across the globe, atmospheric losses are more or less symmetrical. The atmosphere bleeds out evenly, in all directions, slowly. On a tidally locked hot Jupiter, the asymmetry creates these strange, lopsided structures in space. There is something deeply human about this image. A planet bleeds harder on the side that bears the most pain, the side that always faces the heat, the side that cannot turn away, the side that, given enough time, will be the first to dissolve completely. There is another consequence. Because the dayside is losing material faster, the planet is slowly evolving in shape and chemistry. If certain heavier atoms cannot escape as easily as light hydrogen and helium, then over millions of years, the planet's atmosphere may grow chemically richer in heavier elements as the lighter ones flee. That changes the planet's color, its temperature behavior, even its weather. Scientists are now using HAT P67b as a model system to understand these patterns. If we can predict how a tidally locked giant loses gas over time, we can apply the same logic to the thousands of other hot Jupiters out there. Some of those distant worlds could be heading toward the same fate. Some could already be deep in their own helium-leaking endgames. The asymmetric tail is only one strange aspect of this planet. Another comes from how astronomers measure size in the first place. Because, as it turns out, the size you get depends on where you decide the planet ends. And on this planet, that choice is much harder than it sounds. When astronomers talk about the size of HAT P67b, the number that gets quoted most often is 2.14 times the radius of Jupiter, roughly twice as wide. That number comes from measuring how much starlight the planet blocks during a transit in the visible part of the spectrum. But that is not the only number. Depending on what wavelength of light you look at, the planet appears to be a different size. Look at it in normal visible light, and the planet looks like a sphere about 2 Jupiters wide. Look at it at the special infrared wavelength, where helium lights up, and the planet looks much bigger. One study estimated the effective planetary radius at this wavelength to be roughly 6 times the radius of Jupiter. 6 times. That is an enormous jump. It does not mean the planet is suddenly 6 times wider in any solid sense. It means that the gas surrounding the planet, the cloud of escaping helium, is so extensive that when starlight tries to pass through this region, it gets absorbed across a volume 6 times Jupiter's radius. The planet has, essentially, a glowing halo of escaping atmosphere wrapped around it. Looked at in the right kind of light, that halo is part of what counts as the planet itself. This is one of the strange truths of exoplanet science. A planet is not just a hard ball with a clean edge. It is a layered structure. There is the deep interior, where pressure and temperature are extreme. There is the cloud deck, where you might say the planet starts to feel solid in some sense. There is the upper atmosphere, where pressure thins out. And there is the exosphere, the wispy outer reach where individual atoms drift away into space. For a normal planet, all of those layers fit inside a relatively small range. For HAT P67b, the exosphere is so large and so active that it dwarfs the planet's main body. If the planet were a single grape, its escaping atmosphere would be the size of a beach ball wrapped around it. This affects how the planet interacts with its star. From the host star's point of view, HAT P67b is not just a planet, it is a planet plus a cocoon. The cocoon catches more radiation than a smaller object would. It absorbs more starlight. It heats up more aggressively. It feeds back into the planet's overall energy balance, contributing to the same puffiness that produced it in the first place. There is also a beauty hidden in the absurdity of this number. A planet that, by one measurement, is twice as wide as Jupiter, by another, 6 times as wide. The discrepancy is not contradictory, it is layered. It tells us that this world is not a single thing, it is a process, an evaporating, fluctuating, breathing entity. Some astronomers have begun to think of planets like HAT P67b as more like comets than worlds, not in size, of course, but in behavior. The defining feature of a comet is that it leaves a tail because its body is constantly losing material. The defining feature of HAT P67b might also be its loss. Take away the tail, take away the leaking halo, and the planet still exists. Add them in, and the picture is no longer of a sphere. It is of a glowing, smearing entity in motion. The size question, then, is really a question about identity. What do we mean when we say a planet is enormous? Are we talking about the part that you could in principle stand near, the part that you could fall through, the part that would burn you if you got too close? On HAT P67b, those are 3 different sizes. And this distinction matters more than it sounds, because right at the edge of giant planet sizes, there is a boundary that decides whether something is a planet at all. Stars are massive, planets are smaller, easy enough, on the surface. The Sun is a star because it fuses hydrogen at its core. Jupiter is a planet because it does not. There is a clean line, except there is not, between stars and planets. In the strange grey zone of the universe sits a class of objects called brown dwarfs. They are too small to be stars. They are too big to fit the cleanest definition of a planet. They occupy a fuzzy borderland that has caused arguments among astronomers for decades. A brown dwarf is, roughly, an object with a mass between 13 and 75 Jupiters. At 13 Jupiter masses, an object can briefly fuse a heavy form of hydrogen called deuterium. At 75 Jupiter masses, it can begin to fuse normal hydrogen and become a real star. Anything in between is a brown dwarf, glowing with leftover heat from its formation but never igniting full stellar fusion. Here is the strange twist. Brown dwarfs are often smaller than the largest puffy planets. A typical brown dwarf has a radius close to Jupiter's. Some are even slightly smaller because their high mass compresses their interior so tightly that they shrink despite being more massive. So if you measured size alone, a brown dwarf might fit inside HAT P67b with room to spare. Yet the brown dwarf is heavier, more dense, and on the wrong side of the planet definition. This is why HAT P67b matters scientifically. It is one of the largest objects ever confirmed as a true planet. Astronomers had to be very careful with this one, because at first glance, the question of whether it is even a planet at all could have gone in different directions. The mass measurement was the deciding factor. By tracking how the planet tugged on its host star, by combining measurements from radial velocity, transit timing, and Doppler tomography, the team eventually arrived at a planetary mass of roughly 0.45 Jupiter masses, less than half the mass of Jupiter, far below the brown dwarf threshold. There was no real ambiguity. This object, despite its size, did not fuse anything. It was a planet. The contrast is striking. A brown dwarf with the radius of Jupiter could weigh 40 Jupiters or more. HAT P67b has more than twice that radius and weighs less than half of 1 Jupiter. The brown dwarf is small but heavy. The planet is large but light. They occupy almost opposite corners of the same map. There are other contenders for the title of largest known exoplanet. Some objects, like GQ Loopy b, have estimated radii anywhere from 1.8 to over 4 Jupiter radii, with huge uncertainty. Some, like ROX 42BB, have been described as 9 Jupiters in mass and 2.5 Jupiters in radius, but their planet status is debated. Some, like HD100546b, have wildly varying estimates and unclear classifications. What HAT P67b has that none of those others do is clarity. Its size is well measured. Its orbit is well known. Its mass falls clearly in the planetary range. Among confirmed, well-characterized planets, with cleanly resolved sizes, it is the largest single object ever found. That clarity is part of why it is also so disturbing, because if the largest confirmed exoplanet is also one of the lightest, with a dying star, an evaporating atmosphere, and a future engulfment, then the universe is telling us something about how planets behave at their most extreme, something about fragility, something about borrowed time. But there is still one mystery left in this chain, because every model of how this planet should have evolved says it should not still look this way. Something has been keeping it puffy long after it should have deflated, and the explanation, when it finally arrived, sounded almost too simple. Imagine a balloon at a child's birthday party. Air leaks out slowly, hour by hour. By the next morning, it is shriveled and small. The party is over. The balloon's job is done. Now imagine a balloon that has somehow stayed full for a decade. Every model of balloon physics says it should be deflated. Every prediction says the air should have leaked out long ago, and yet it sits there, plump and round, defying expectations. That is HAT P67b. The standard models of low-density hot giants predict that a planet with this density, this temperature, and this proximity to its star should lose its atmosphere within 100 million years or so. After that, what remains would be a small, dense core, surrounded by either a thin envelope or nothing at all. The numbers are clear. The physics is well understood, and yet, HAT P67b has somehow held on for over 1 billion years. The recent breakthrough in understanding comes from a careful look at the host star. The star is not a stable, calm, middle-aged sun. It is a subgiant. It has recently entered a phase of expansion, swelling, and brightening as its core hydrogen runs out. This phase is dramatic on stellar timescales. Over a few 100 million years, the star can grow significantly larger and pour out far more energy than it did during its main lifetime. The implication is fascinating. HAT P67b might not have always been a puffy, leaking giant. For most of its life, when its star was younger and quieter, the planet may have been smaller, denser, and more stable. Then, recently, in cosmic terms, the star started its dying phase. The radiation poured out at higher levels. The planet's atmosphere, suddenly receiving far more heat, began to inflate. This means we are not looking at a planet at the end of its life. We are looking at a planet at the beginning of a new, violent phase. The puffiness is a recent development. The mass loss has only recently kicked into high gear. The dramatic helium tail is a relatively young feature, perhaps only tens of millions of years old in its current form. This explains the puzzle of the planet's age. It has not been losing atmosphere for 1 billion years. It has been losing it for a much shorter window. The total amount of gas lost, while still enormous, is not as catastrophic as it would be if the leak had been running at full speed since the planet's formation. The planet is dying, but the dying has just started. This new framework also predicts the future. If the host star continues to swell, the radiation will keep increasing. The planet will keep inflating. The mass loss rate will keep climbing. At some point, the rate will become so extreme that the planet will simply not be able to hold onto its atmosphere at all. The envelope will be stripped completely. The bare core, if there is one, will be exposed to the open glare of the now red giant star. After that, gravity does the rest. The bare core, if any, gets pulled inward. Tidal forces tear it apart. The remains spiral down into the swelling star and are absorbed. There is a strange comfort in this picture. The planet is not an aging marvel slowly dying for billions of years. It is a newly inflated giant, riding the wave of its star's death, glowing brilliantly for the brief window of cosmic time between the start of its star's expansion and the end of its own existence. It is having its big moment, right now. On the human scale, that moment will last hundreds of millions of years. On the cosmic scale, it is the blink of an eye. There is an invisible boundary around every star. It is called the Roche lobe. Inside this boundary, an object can hold itself together against the star's gravity. Outside this boundary, the star wins. Material gets pulled away, ripped from the object, drawn toward the star. For most planets, the Roche lobe is far away. Earth, for example, sits well inside the Sun's Roche lobe. There is no danger of our planet being pulled apart by solar gravity. The same is true of every planet in our solar system. They are all comfortably distant from any boundary where stellar tides become destructive. P67b is not so lucky. The planet is so close to its star, and the star is in such a violent phase of expansion that the Roche boundary itself is moving. As the star swells, its gravitational reach grows. The Roche lobe stretches outward. The planet, which once may have been comfortably inside the safe zone, is now hovering near the edge. If the planet's atmosphere extends past the Roche lobe, gas in that region no longer fully belongs to the planet. It belongs, gravitationally, to the star. Such gas streams away, channeled toward the star, in a process called Roche lobe overflow. It is one of the more dramatic ways that mass can flow between objects in a tight stellar system. There is some debate over whether P67b is actively in Roche lobe overflow right now. The lower limit on its mass, set by the assumption that it is not, is one indirect way astronomers have constrained the planet's properties. If the mass were significantly lower than it is, the planet would be too inflated to fit inside its own Roche lobe, and it would be tearing apart faster than current observations suggest. But the planet is dancing close to that boundary. As the host star continues to expand, the boundary continues to shrink relative to the planet's atmosphere. The planet's outer layers are increasingly exposed. The leading helium tail itself may be partly the result of gas from the dayside drifting past the Roche limit and getting caught in the star's gravitational field. This sets up a cascading process. Atmosphere passes the Roche boundary and gets pulled. The pull increases the rate of loss. The rate of loss thins the upper atmosphere. The thinning lets more atmosphere expand outward, exposing yet more gas to the boundary. Once the cycle starts in earnest, it accelerates. A planet does not slowly fade. It tips into a runaway phase of stripping, losing its atmosphere faster and faster as time goes on. This is one of the futures that may be waiting for P67b. Not a slow, gentle deflation, but a runaway moment, sometime in the next 100 million years, when the planet finally crosses a final threshold and begins to come apart in a much more violent way. After the atmosphere is gone, what remains depends on whether the planet has a solid core. If it does, that core might survive briefly, orbiting the bloated star as a small, dark companion, naked and exposed, until tidal forces drag it inward. If the planet has no significant core, just a continuous gradient of heavy elements deep within hydrogen, then there may be nothing left at all. The planet would simply dissolve. Either way, the end is not gentle. The end is a star reclaiming what it once let go. The end is a giant being torn apart, layer by layer, until the universe holds no record that it was ever there. Except, of course, in the data archives of telescopes that watched the dying flicker, and the scientists who realized what they were seeing, there is a clue hidden in P67b's orbit that tells a different kind of story. A story not about death, but about birth. A story about how this planet got to where it is in the first place. Hot Jupiters, planets the size of Jupiter or larger orbiting closer than Mercury, are puzzles. They cannot have formed where we find them. The region near a star is too hot for the icy materials needed to build a giant planet's core. Gas giants are built in cold places, far out in the disk of dust and gas around a young star. Then somehow, they end up close. The question is how? There are two main scenarios. The first is gentle. The young giant forms in a cold orbit, then drifts inward through the disk itself. The disk drags on the planet, exchanging momentum, slowly spiraling it closer to the star. By the time the disk dissipates, the planet has settled into a tight orbit, neatly aligned with the star's equator. The whole process is calm, smooth, and orderly. The second scenario is violent. The young giant forms far out, then gets a gravitational kick from another planet or a passing star. Its orbit is twisted, stretched, pulled into a tight arc. Over millions of years, tidal forces with the host star circularize the orbit, but the alignment is often messy. The planet ends up on a tilted path, sometimes even an orbit that goes the wrong way around the star, opposite to the star's own rotation. How a hot Jupiter aligns with its star is a fingerprint of how it got there. HAT P67b's orbit is almost perfectly aligned. The angle between the planet's orbital plane and the star's equator is only about 2 degrees. 2 degrees out of 180 possible. That is essentially flat. There is almost no tilt at all. This points strongly to the gentle scenario. The planet most likely drifted inward through the disk during the early years of the system's life, slowly spiraling toward the star without any chaotic gravitational interaction. It arrived gently. It settled gently. It has been orbiting in this peaceful configuration for over 1 billion years. There is something poetic about this. A planet that is now suffering one of the most violent fates in the galaxy, getting torn apart by a swelling star, originally arrived through one of the most peaceful migration mechanisms known. It did not get there through chaos. It got there through patience. It rode a slow, steady current of gas inward and settled into orbit like a leaf landing on a quiet pond. The aligned orbit also tells us something about the system's history. There are no signs of recent gravitational encounters with other large planets. There are no indications of nearby stellar passes. The system has been more or less stable for its entire life. This is in contrast to many hot Jupiter systems, where messy orbital evidence suggests violent histories. The aligned orbit even helps with predictions. Planets that are tidally locked in circular orbits, with no recent disturbances, tend to evolve in predictable ways. Astronomers can model their atmospheres, their heat budgets, their loss rates, with relatively high confidence. HAT P67b is, in many ways, an ideal test case for theories of hot Jupiter behavior. It is extreme, but it is also clean. Its history is simple, even as its present is dramatic. This combination of simplicity and extremity is why so many telescopes are now turned in its direction. It is a giant, glowing laboratory hanging in the night sky of Hercules, a bloated, leaking world that fits enough into theory to be useful and breaks enough rules to be interesting. But the planet's orbit is far from the only thing that places it in a strange family. Across the galaxy, there are other puffy planets. Some are even less dense. Some are smaller, but stranger. Together, they form a class of worlds that no one in human history could have predicted before the telescope started looking. HAT P67b is not alone in its strangeness. Across the Milky Way, scattered among the thousands of confirmed exoplanets, sits a small but growing family of worlds with the same defining trait: enormous radius, tiny mass, densities so low they sound made up. Astronomers call them puffy planets, or hot Saturns, or, in the most extreme cases, super puffs. They are the ghosts of the gas giant world, worlds that should not exist according to classical models, and yet keep showing up in the data again and again, each one stranger than the last. One of the early shockers in this family was a planet called WASP-17b. Discovered in 2009, it has a radius around 2 times that of Jupiter, much like HAT P67b, and a mass of only about half a Jupiter. It also has a wildly tilted orbit, going almost backwards around its star, the opposite of HAT P67b's gentle alignment. 2 giants of similar size, with completely opposite arrival stories. Another puffy giant is TRES-4b, discovered in 2007. At one point, it held the title of the largest known exoplanet before HAT P67b took the crown. TRES 4b, has a radius of about 1.8 Jupiters and a mean density similar to balsa wood. It also has, according to early studies, a possible comet-like tail of escaping atmosphere. Sound familiar? Then there is WASP 193b, announced more recently. This one has a radius of about 1.5 Jupiters, but only 14% of Jupiter's mass. Its density is similar to cotton candy. It is so puffy and so light that it occupies a part of the planet space that current models cannot easily explain. Some theorists have proposed that an unusual heat source deep inside the planet might be holding it open. Others suggest the planet is in a brief, anomalous phase of inflation that will end soon. There is also a small set of even more extreme planets called superpuffs, worlds with masses similar to Neptune but radii similar to Jupiter or larger, densities of 0.05 grams per cubic centimeter or even less. The poster child of this group is Kepler 51d, with a density less than a tenth of water. Its sibling planets, Kepler 51b and c, are similarly absurd. What ties this family together is not just low density. It is the shared sense that these planets break the rules of how giants are supposed to evolve. They are too big, they are too light, they lose mass too quickly, they survive too long. They suggest that the universe has more ways to make planets than we yet understand. There is also a quiet trend in the data. Many of the puffiest planets orbit aging stars. Stars that, like HAT P67, are in their subgiant phase or just past it. The link makes physical sense. As stars age, they pour out more energy. Their close orbiting planets get hit harder. Atmospheres swell, densities drop, the planets puff up just as their stars start to die. In a sense, puffy planets may be a kind of cosmic snapshot, a specific moment in the joint life of a star and its closest companion, a brief, dramatic interval where a planet that was once normal becomes something extraordinary just before it is destroyed. HAT P67b sits at the extreme end of this snapshot, the largest of the puffy giants, possibly the most dramatic loss rate, possibly the closest to its eventual end, a poster child for an entire class of planets that we are only beginning to map. Some of these worlds are even stranger than HAT P67b in specific ways. One, in particular, has been compared in research papers to a substance found at children's birthday parties. Cotton candy, spun sugar, pink fluff sold at fairs and circuses. It is one of the lightest substances most humans ever hold. Pull a tuft of it apart and it dissolves into wisps of nothing. Hold it in damp hands and it shrinks into a sticky droplet smaller than a marble. It is mostly air and the suggestion of sugar. The density of cotton candy is around 0.05 grams per cubic centimeter. There are planets in our galaxy with densities lower than that. The most famous example is Kepler 51d, a planet about 40 light-years from Earth in the constellation Cygnus. It is part of a system of 3 planets, all of them puffy beyond reason. Kepler 51d has a mass of only about 5.5 times that of Earth, a small mass, yet its radius is over 9 times Earth's, about 9/10 the radius of Jupiter. The combination produces a density of about 0.046 grams per cubic centimeter, less than cotton candy. WASP 193b, the planet mentioned earlier, has a similar density of about 0.059 grams per cubic centimeter, slightly denser than Kepler 51d, but still in the cotton candy range. HAT P67b sits at about 0.061 grams per cubic centimeter. All 3 planets are within the same band of impossibility. What does it actually mean to have a density that low? Imagine a planet the size of a small skyscraper, weighing less than the bricks that make up its foundation. Imagine an object the size of Mount Everest, weighing less than a single boulder rolling at its base. Imagine the entire mass of the planet packed into a vast, hollow-looking sphere of warm gas, held together only because gravity, even weak gravity, eventually wins. Standing on the surface of such a planet, if there even were a real surface, would feel almost like floating. The gravitational pull of HAT P67b is much weaker at its outer edge than gravity on the surface of Jupiter. A person standing in the upper atmosphere would feel only a fraction of Earth gravity. They could leap with a casual push and stay airborne for what would feel like minutes. The atmosphere itself would flow past them like a slow, hot wind. Cotton candy worlds are also where the boundary between planet and atmosphere blurs. On Earth, you can clearly say where the rock ends and the air begins. On Jupiter, the boundary is fuzzier, but the planet still has a dense interior far below the visible cloud tops. On a cotton candy planet, the entire visible structure might be atmosphere all the way down. There may be a small core deep inside, but most of the planet's volume is just gas, getting denser as you descend, getting hotter as you descend, blending continuously from sky to interior with no clear transition. These planets challenge how we imagine alien worlds. Most science fiction shows planets as solid spheres with cities, oceans, and skies neatly stacked. Cotton candy planets do not work like that at all. They are puffs, globes of nearly empty gas. They look more like glowing cumulus clouds than the dramatic landscapes most stories assume. There is something almost gentle about this image. A planet so light that it would barely tug at a hand. A planet that bleeds into space because its grip on its own atmosphere is so soft. A planet built more out of suggestion than substance. But a planet this puffy is also dangerously fragile. A small shove from gravity, a slight increase in stellar radiation, and the whole structure can shift dramatically. The closer such a planet sits to its star, the faster it loses material. The further it sits, the more mysterious its inflation becomes. There is no model that makes them stable for long. For HAT P67b, with its tight orbit and dying host star, the fragility is at its peak. And measuring this kind of planet, especially its mass, turned out to be one of the longest scientific dramas in modern astronomy. When astronomers want to know how massive a planet is, they usually use a technique called the radial velocity method. The idea is simple. As the planet orbits, it tugs gently on its host star. The star, in turn, wobbles. By watching the star's light shift slightly back and forth, scientists can measure the wobble and calculate how massive the unseen planet must be. For most stars, this technique works beautifully. The host star is calm, its light is stable, and the wobble caused by an orbiting planet stands out clearly. A few weeks of observation is often enough. HAT P67 was a different beast. The host star spins very fast. Its rotation broadens its spectral lines until they are smeared across a wide range of wavelength. Trying to measure a small wobble in such a smeared signal is like trying to detect a faint whisper in a room full of shouting people. The signal is there, but the noise overwhelms it. Worse, the star is also active. Its surface flickers, pulses, and shows signs of complex activity. Some of those activity patterns can mimic the signal of an orbiting planet, leading to false positives. Some can hide a real planet entirely. Untangling the planet from the star's own behavior took years. The first attempts to measure the mass of HAT P67b began in 2009. They produced only an upper limit. Researchers could say that the planet was less massive than a brown dwarf, but they could not pin down a specific number. The data was consistent with a wide range of masses, including some that were absurdly low. By 2012, observations using the Keck telescope had narrowed it down. The mass was less than 59% of Jupiter's. Still not a precise value, still a ceiling rather than a measurement. For 4 more years, scientists tried different combinations of instruments and analysis techniques. They used multiple telescopes. They modeled the star's activity. They tried to mathematically subtract the noise. The mass kept slipping through their fingers. The breakthrough came in 2016, when a team used a technique called Doppler tomography. Instead of trying to measure the wobble of the star, they directly tracked the shadow of the planet as it crossed the star's surface during a transit. This worked even with a fast-spinning star, because the shadow has a clean, unambiguous shape. The technique confirmed that the transiting object was indeed a planet, not a stellar artifact, and it gave the first solid mass constraint. But even then, the precise mass was not nailed down. It took until 2025 for a team using the NIDE spectrograph on the WIYN telescope, paired with new methods to handle the star's activity, to obtain a planetary mass of 0.45 Jupiter masses, plus or minus 0.15. Combined with the well-known radius of 2.14 Jupiter radii, this gave a clean density of about 0.06 grams per cubic centimeter, almost 2 decades. From the first hints of a strange dimming pattern, to the first attempts to measure mass, to the final cleanly published value, the journey took the better part of a generation. It is a useful reminder of how difficult exoplanet science can be. From light years away, with a noisy star spinning fast and a planet that defies easy models, the simplest question of how much something weighs can take humanity years of telescope time to answer. Each observation is a small victory. Each refinement is a step forward in mapping something that no human will ever visit. The mass measurement also confirmed something important. With a density that low, this planet is not just one of the largest ever found. It is one of the lowest density hot giants known, second only to a small handful of competitors. It is officially in the most extreme corner of the planet's space, where the rules of physics seem to have written themselves new exceptions. Doppler tomography sounds like a technique from a science fiction novel. It is actually one of the more elegant ideas in modern exoplanet science. The technique watches not the wobble of a star, but the shape of the star's spectral lines as a planet transits across the surface. When a star spins, the surface on one side moves toward us, and the surface on the other side moves away. The light from the side moving toward us is shifted slightly toward bluer wavelengths. The light from the side moving away is shifted slightly toward redder wavelengths. The combined effect smears the spectral lines into a broad shape that contains, in a hidden way, a map of the star's surface. When a planet transits the star, it covers up a small piece of the star's disk. That piece has a specific velocity signature. By blocking it, the planet removes a specific, narrow part of the spectral line. As the planet moves across the star, the missing piece moves too, sliding from blue to red. The shape of the spectral line changes in a clean, predictable way. This is Doppler tomography. The shadow of the planet, traced through the spectrum, frame by frame, like a fly walking across a flashlight beam. For HAT P67b, this technique was crucial. The host star's rapid rotation, which made traditional radial velocity measurements so difficult, actually helped Doppler tomography work better. A faster spin means a wider spectral line, which means more room to see the planet's shadow move across. In 2016, a team used Doppler tomography to definitively confirm HAT P67b as a real planet, not an artifact of stellar activity. The shape of the shadow matched what would be expected from a transiting body. The motion of the shadow matched the orbit of the supposed planet. The planet was real. It had been detected, doubted, and finally caught in the act of crossing its star. The same method, applied carefully, also revealed the alignment of the planet's orbit. By tracking exactly which parts of the spinning star the shadow covered first and last, scientists could measure how the orbital path tilted relative to the star's equator. The result was the famous 2-degree alignment that pointed to a gentle migration history. There is a beauty in this technique that goes beyond science. It is a way of seeing something invisible by watching what it removes. The planet is too small and too far to image directly, but the absence of light, the gap it leaves in the spectrum, is enough to map its motion in detail. The planet is studied not by what it shows, but by what it hides. This kind of indirect detection is the heart of modern exoplanet science. We have only ever directly imaged a small fraction of known exoplanets, mostly the largest, brightest, and most distant from their stars. Hot Jupiters are usually invisible against the glare of their host stars, but they leave traces, tiny dips in light, wobbles in spectra, shadows on rotating disks. From those traces, we reconstruct everything we know about them. For HAT P67b, the shadow on the spinning star was the moment when it passed from being a candidate to being a confirmed reality. Before that, it was a tantalizing pattern in the data. After that, it was officially the largest planet humans had ever confirmed. The same observations, refined and expanded, also unlocked another famous trick in exoplanet science. A trick named after two scientists who first imagined it more than a century ago. In 1924, two American astronomers named Richard Rossiter and Dean McLaughlin independently published papers describing a strange effect in eclipsing binary stars. When one star passed in front of another, the spectral lines of the eclipsed star would shift in a specific, predictable way. The effect was subtle, mostly forgotten by all but a few specialists. Almost a century later, this same effect would become one of the most powerful tools in exoplanet science. Here is what happens. As a star spins, half its surface moves toward us, half moves away. When something covers up part of the spinning star, it covers up parts that have specific velocities. If a planet first covers the side of the star moving toward us, the average light from the star will shift slightly toward redder wavelengths because we are losing light from the blue-shifted side. Then, as the planet crosses to the other side, the effect reverses. The star appears to shift slightly toward blue. By measuring this shift carefully during a transit, astronomers can tell which path the planet takes across the star. They can tell whether it crosses the equator, a pole, or somewhere in between. They can measure the angle between the planet's orbital plane and the star's spin axis. This is the Rossiter-McLaughlin effect. It is one of the cleanest tools available for studying the alignment of planetary orbits. For HAT P67b, the application was straightforward in concept, even if difficult in practice. By observing transits with high-precision spectrographs, scientists tracked the velocity shifts during the planet's crossing. They modeled the expected pattern for a perfectly aligned orbit. They modeled the pattern for a tilted orbit. They compared the actual observations to both models. The match was almost perfect with the aligned scenario. The angle between the orbit and the equator came out to about 2.2 degrees, with an uncertainty of less than half a degree. This is the most precisely aligned hot Jupiter system known to date. This is more than a technical curiosity. The alignment is a direct fingerprint of the planet's history. A system that experienced violent gravitational kicks during its formation would almost certainly show a tilted orbit. A system that arrived through gentle disk migration would show an aligned one. HAT P67b is firmly in the gentle camp. The contrast with other hot Jupiters is striking. WASP-17b, the comparable puffy giant mentioned earlier, has a strongly retrograde orbit. It moves backward around its star. The angle between its orbit and the equator is more than 100 degrees. Two giants with similar size, similar density, similar broad properties, but completely opposite arrival stories. This tells us something important. Puffiness does not depend on how a planet got to its star. It depends on what happens once it arrives. Two planets can take wildly different paths to their final orbits, and yet both end up bloated and leaking, as long as they end up close enough to a hot enough star. The Rossiter-McLaughlin technique has now been applied to hundreds of hot Jupiters. The results have transformed how astronomers think about the dynamical histories of planetary systems. Some systems are calm, some are violent. Many show signs of past chaos. A few, like HAT P67, look like quiet survivors. Looking at HAT P67b through the Rossiter-McLaughlin lens, the planet emerges as a peaceful migrant, a giant that drifted calmly into a tight orbit. It has been sitting there for 1 billion years, waiting for the slow expansion of its star to begin the process of its destruction. There was no early chaos, There was no last-minute rescue, just a long, quiet stretch of orbiting, followed by a violent end, which leads to a deeper question. How did such a giant form in the first place, before it ever migrated anywhere? A gas giant cannot form near a star. The temperature is too high. The materials needed to build a giant's core, water ice, methane ice, and ammonia ice, would all be vapor at the temperatures found in the inner regions of a young system. A solid core cannot grow there. This means every hot Jupiter, including HAT P67b, was born somewhere else. The standard story goes like this. A young star is surrounded by a disk of gas and dust. In the inner regions, temperatures are high. Only rocky and metallic materials can condense. In the outer regions, beyond a boundary called the snow line, temperatures are cold enough for water ice to form solid grains. These grains stick together, build into pebbles, then boulders, then mountains, then small planetary cores. When a core grows large enough, around 10 Earth masses, it can start pulling in gas from the disk. Hydrogen and helium flow inward, wrapping the core in a thick atmosphere. The core continues to accrete material until either the gas runs out or the disk dissipates. The result is a gas giant. Jupiter, Saturn, and most cold giants in the universe are thought to form this way. HAT P67b probably started this way too. Far out, beyond its star's snow line, a small icy core grew. Then, gas from the disk poured in. The core became a giant. It probably resembled a young Saturn or Jupiter, sitting peacefully in a wide, cold orbit. But the planet did not stay there. Something happened to it. The most likely process is disk migration. As the planet sat in its young orbit, it interacted gravitationally with the surrounding disk. The disk was massive. The planet was massive. They pulled on each other. Spiral density waves formed in the disk near the planet, like the wake behind a boat in a pond. These waves carried away angular momentum from the planet. The planet, losing angular momentum, drifted slowly inward. Over millions of years, the drift carried HAT P67b from its birthplace, somewhere far out in the system, into its current tight orbit. The migration was slow, gentle, and never broke the alignment between the planet and the star's equator. By the time the disk dissipated, the planet was already locked into its present location. This story is consistent with everything astronomers can measure about the planet today. The aligned orbit, the circular shape of the orbit, the lack of evidence for nearby companions that could have provided gravitational kicks. But there is one detail that the standard story does not fully explain. Why is HAT P67b so much bigger than other hot Jupiters? Why is it twice the size of Jupiter, while most others are only slightly bigger than Jupiter at most? The answer probably lies in the recent expansion of the host star. The planet was likely a normal hot Jupiter for most of its life, about the size of Jupiter, maybe slightly larger. Then, as the host star transitioned into its subgiant phase, the radiation poured out at much higher levels. The planet's atmosphere, sensitive to the increased heat, began to inflate. Over a few 100 million years, the planet swelled to its current absurd size. In other words, what we see today is not the original HAT P67b. It is the inflated, late-life version. The planet was born as something more conventional. It is dying as something extreme. This idea has implications for the entire field. If hot Jupiters around aging stars are systematically more inflated than hot Jupiters around young stars, then the population of puffy giants is probably much larger than astronomers initially thought. Many of those puffy planets are simply normal giants caught in the expansion phase of their host stars, on their way to similar fates. The galaxy may be full of inflating planets, each one in its own private end-of-life drama. HAT P67b is just the brightest, clearest, easiest to study example. Disk migration sounds simple in summary. A planet drifts through a disk of gas and dust until it reaches a closer orbit. In practice, the physics is rich and strange. There are several distinct flavors of migration, each with its own quirks, and a hot Jupiter like HAT P67b probably went through more than one. The first type is called Type 1 migration. It happens when a planet is small enough that its gravity does not dominate the local disk. Spiral density waves form in the disk on either side of the planet. These waves carry angular momentum, mostly outward. The planet, in response, slowly drifts inward. Type 1 migration tends to be fast for small planets. It is the most likely fate of an Earth-mass world embedded in a young disk. The second type is called Type 2 migration. It happens when a planet grows large enough to carve a clean gap in the disk around its orbit. Once the gap forms, the planet is no longer free to interact with most of the disk material. Instead, the planet locks itself to the disk's evolution. It drifts inward at the rate that the disk itself is contracting under viscosity. Type 2 migration is slower than Type 1, but it can deliver a giant planet from far out in a system to a tight orbit in just a few million years. A planet like HAT P67b, with a mass close to half of Jupiter, would have carved a gap during its young years. Type 2 migration would have taken over. The planet would have ridden the slow inward flow of the disk, like a leaf caught in a current, for a few million years until it arrived in its present orbit. There is a third category, called disk-free migration, where planets are flung inward by gravitational scattering from other planets or stars. This is the violent path. It tends to leave tilted, eccentric orbits. HAT P67b shows no sign of this kind of history. What stops migration? This is one of the hardest questions in planetary formation theory. Once a giant starts moving inward, what prevents it from spiraling all the way into the star? There are several possible answers. The disk eventually dissipates. The disk's inner edge can act as a barrier. Tidal interactions with the star can slow the migration. Resonances with other planets can lock the migration into a stable configuration. In most observed systems, hot Jupiters end up at distances of about 0.05 astronomical units, suggesting that the inner edge of the disk acts as a natural stopping point. HAT P67b sits at 0.065 astronomical units, slightly outside the typical hot Jupiter zone, but well within the migration range. Likely, it stopped at the inner edge of its own protoplanetary disk and has been sitting there ever since. There is something almost peaceful about this image. A young planet, born in a cold place, slowly drifting through a swirling cloud of gas and dust, finding its place at a stable orbital distance. Then, billions of years later, the same star that nurtured it begins to grow and threatens to swallow it. The planet outlived the disk that birthed it. It outlived the dynamic chaos of the system's youth. It survived asteroids, comets, and any close passes by other stars. Through all that, it sat in its tight orbit, patient, quiet, inflated only because of the recent stellar drama that is now sealing its fate. Standard theory predicts that this fate is shared by many hot Jupiters. If a star ages enough, its closest planets will eventually be engulfed. There are even direct observations of planets being eaten by their stars, captured as faint flares of light in the night sky. The galaxy is full of these slow consumptions, happening at different rates around different stars, each one ending the story of a planet that spent billions of years orbiting peacefully before the end. For HAT P67b, that end is no longer abstract. It has a timeline. How long does HAT P67b have left? The answer depends on whom you ask, what model they prefer, and which assumptions they make. But the broad picture is consistent across studies. Sometime between 150 and 500 million years from now, the planet will be tidally disrupted or engulfed by its host star. That number sounds like an eternity. In human terms, it is. The entire history of mammals on Earth, from the earliest tiny shrew-like creatures of the late Cretaceous to today, fits inside about 200 million years. The dinosaurs ruled for roughly the same span. Continents have shifted, oceans have opened and closed, ice ages have come and gone, all within timescales of a few 100 million years. HAT-P67b has, at most, about that much time left. Here is what is going to happen, in stages. The first and most immediate effect is the loss of atmosphere. The planet is already bleeding helium and hydrogen into space. As the host star continues to expand and brighten, the rate of mass loss will increase. The planet's outer layers will inflate even more. The Roche limit will close in. At some point, the rate of loss will become so extreme that the planet's atmosphere cannot keep up. It will be stripped, layer by layer, faster than it can replenish itself. At the same time, the host star itself will keep growing. Stars in the subgiant phase do not stop expanding. They keep getting bigger until they are several times their original size. Eventually, the star will become a true red giant, with a surface that engulfs the inner regions of its planetary system. By then, HAT-P67b will be long gone, but the star's expansion is what sets the timeline. Estimates of the planet's atmospheric lifetime vary. At current loss rates, the atmosphere would survive for several 100 million years. But the loss rate is not constant. As the star brightens, the loss rate accelerates. Some models predict that the atmosphere will be effectively stripped within 150 million years. Others, more conservative, give the planet up to 500 million. After the atmosphere is gone, what remains is the planet's deep interior. If there is a small, rocky or metallic core inside, that core would briefly survive. It would orbit the now red giant star as a small, dark, exposed body. The light reaching it would be enormous. The temperature would be staggering. Tidal forces from the bloated star would tug at it relentlessly. The core would not last long. Within tens of millions of years, possibly less, it would spiral inward through gravitational drag and tidal forces. It would cross into the swelling outer atmosphere of the host star. There, friction would decelerate it. It would heat up to extreme temperatures, glowing white-hot. Eventually, it would be torn apart and absorbed. This kind of event has actually been observed. In 2023, astronomers reported the direct detection of a planet being engulfed by its star, creating a brief flash of light visible from Earth. The flash was the death cry of a world. HAT-P67b is on track for the same kind of end. The whole process, from now to total absorption, will probably take less than 1 billion years. After that, nothing will remain. The planet will not be a memory in the universe. It will be matter mixed into the atmosphere of an aging star. Some of its hydrogen and helium will eventually be returned to the interstellar medium when the star sheds its outer layers in its final breaths. But the planet itself, as a distinct object, will be gone. There is something terrible and beautiful about this. The planet is dying right in front of us. We are watching it. We are studying it. We are recording its last few 100 million years of existence in real time. By the time the next sentient species, if any, looks at this part of the sky, the planet will be a nameless fossil in the data archives of long-dead civilizations. What does it actually look like when a star eats a planet? The process, in detail, is one of the most violent astronomical events that can happen to a world. It happens in stages, each stage longer than human history, each stage erasing more of what was once a complete and stable planet. First comes the swelling. The host star has been gradually expanding for hundreds of millions of years already. As it transitions deeper into its red giant phase, the expansion accelerates. The star grows from its current size into something dozens of times larger. The outer layers cool, redden, and become more diffuse. From a great distance, the star changes color from white to orange to deep red. As the star expands, the planet does not just stay where it is. The orbit slowly evolves. Tidal forces between the bloated star and the planet drag the planet inward, decade by decade. By the time the star has grown to several times its original radius, the planet's orbit has shrunk to match. The planet is closer than ever. The heat is more intense than ever. The atmosphere is bleeding faster than ever. Second comes the contact. At some point, The star's outer atmosphere reaches outward enough to actually touch the planet. This is not a sharp boundary. The star's outer layers are extremely thin, so thin they would not feel solid by any earthly measure, but they are made of hot, glowing gas. As the planet plows through this gas, friction begins. The planet is no longer orbiting in a vacuum. It is orbiting through a medium. The friction does two things. It heats the planet's outer layers even more, accelerating the loss of atmosphere. It also acts like air resistance, slowing the planet down. With each orbit, the planet loses a tiny bit of orbital energy. The orbit shrinks faster. Third comes the spiral. Once the planet is fully embedded in the star's outer atmosphere, the contraction accelerates dramatically. The planet's path becomes a spiral inward, drawn ever tighter, ever faster, by the friction and the gravitational pull of the star's denser interior. The spiral may take thousands of years from start to finish, but in cosmic terms, it is the final plunge. As the planet spirals deeper, the surrounding gas gets denser and hotter. The planet's atmosphere is stripped completely, then the deeper layers begin to vaporize. Hydrogen and helium are absorbed into the star. Heavier elements, if present in the planet's core, are heated to temperatures that dissociate molecules and ionize atoms. Fourth comes the disruption. At some point, tidal forces from the star become strong enough to physically tear the planet apart. The planet's gravity can no longer hold its own pieces together against the stretching pull of the star. The remaining body of the planet shatters into pieces, each piece following its own slightly different path. The shattered pieces are absorbed, one by one, into the star's atmosphere. Some are vaporized within minutes. Others, if they happen to be heavier or denser, sink slowly through the star's outer layers like stones in honey, melting and dissolving as they go. Fifth and final comes silence. When the last piece of the planet has been absorbed, there is no record left. The star may briefly brighten because of the additional energy from the planet's destruction. Astronomers observing such an event might see a short flare, a small spike in luminosity, a slight change in the star's chemistry. Beyond that, nothing. A planet that took billions of years to form, and existed for billions of years more, is erased in a process that, on the cosmic clock, takes a few 100,000 years at most. For HAT P67b, this is the future waiting in the dark. The signs are already there. The planet is bleeding. The star is swelling. The countdown has started. Sometime in the next few 100 million years, this entire cycle will play out exactly as predicted, exactly as described. The universe will lose one of the most distinctive planets ever known. When astronomers talk about studying a planet they cannot reach, they often describe the work as reading fingerprints. Light from the host star passes through the planet's atmosphere on its way to Earth. Different molecules in the atmosphere absorb light at different wavelengths. Each molecule leaves its own pattern in the spectrum. The patterns, taken together, are the fingerprints. For HAT P67b, the most famous fingerprint is helium. The helium absorption signal at a wavelength of 1.083 microns is a classic feature of escaping atmospheres. It is almost a unique tracer for atoms in the upper atmosphere of a hot giant. When astronomers see this signal during a transit, they know they are looking at gas that is high enough in the atmosphere to be on the edge of escaping. But the signal is not just present at HAT P67b, it is huge. The absorption is so strong that, as mentioned earlier, the effective planetary radius at this wavelength stretches to several times Jupiter's. The planet is, in helium light, enormous. The signal lingers before and after the planet's transit, suggesting a vast cloud of gas wrapped around and trailing behind the planet. Another important fingerprint is hydrogen. Hydrogen leaves several distinctive absorption signals in the ultraviolet and visible parts of the spectrum. The Lyman alpha line of hydrogen in the ultraviolet has been used to study escaping atmospheres on other hot Jupiters. For HAT P67b, observations targeting hydrogen are ongoing. If the planet is losing hydrogen as fast as the helium data suggests, the hydrogen signature should also be enormous. There are other fingerprints scientists are searching for too. Magnesium, iron, sodium, potassium, and various molecules have been detected in the atmospheres of other hot Jupiters. For HAT-P67b, current observations have found no clear evidence of atomic or molecular species in the optical range, beyond the helium signal. This is somewhat unusual. It may mean that the day side is hot enough to dissociate or ionize most molecules, leaving the atmosphere chemically simple. Some studies have suggested signs of activity related to the host star. The star is rotating fast and shows pulsational features. Some of the apparent absorption signals around the planet may actually be artifacts of stellar activity rather than real planetary features. Disentangling the planet from the star is one of the most difficult parts of this kind of science. Every observation has to account for what the star is doing at the same time. The clearest signal, the helium tail, has held up across multiple observations and multiple instruments. It is the most reliable atomic fingerprint of HAT-P67b. The size, structure, and behavior of the tail are now used to test models of atmospheric escape. There is a lesson here for the broader study of exoplanet atmospheres. Even a planet like HAT-P67b, with the most dramatic mass loss yet observed, can be hard to study in detail because the host star contributes so much complexity. The future of the field depends on developing techniques that can separate planetary signals from stellar ones with high precision. This is where the next generation of telescopes will come in. With more sensitivity, more wavelength coverage, and better stability, instruments like the James Webb Space Telescope and upcoming Hubble follow-up programs will be able to search for fainter fingerprints. They might detect specific molecules in the upper atmosphere. They might detect changes in the tail over time. They might even detect rare elements being dragged out of the planet's interior by the relentless mass loss. For now, helium is the loud, clear voice in the data. It says one thing, over and over, every time astronomers look: the planet is losing atmosphere, fast, right now, and it has nowhere to hide from what is coming. The James Webb Space Telescope sits in orbit nearly 1 million miles from Earth, at a gravitationally stable point called L2. Its huge gold-coated mirror, 18 hexagonal segments forming a single light-collecting surface, can see infrared light with unprecedented sensitivity. It is the most powerful space telescope humanity has ever built. JWST is one of the instruments now planned to study HAT-P67b in greater detail. The Hubble Space Telescope, older but still incredibly capable, is also being aimed at the planet. Hubble's strength is in the ultraviolet and visible parts of the spectrum, where it can detect the hydrogen signatures of escaping atmospheres. Together with JWST's infrared sensitivity, the two telescopes are expected to provide the most detailed picture yet of how this planet is losing mass. There are also ground-based observatories playing a role. The Hobby-Eberly telescope in Texas continues to monitor the planet. The Telescopio Nazionale Galileo in the Canary Islands, with its high-resolution spectrographs, has been studying the planet's transmission spectrum. The WIYN telescope in Arizona, with the NEID instrument, recently provided the cleanest mass measurement to date. Each telescope contributes a different piece of the puzzle. Some are good at measuring radial velocities. Some are good at measuring the shape of transit light curves. Some are good at high-resolution spectroscopy of escaping gas. Some are good at imaging the host star to monitor its activity. Together, this network of instruments forms a kind of astronomical surveillance team. Every few months, somewhere on Earth or in orbit, an instrument is pointed at HAT-P67b. Data is collected. Light curves are processed. Spectra are extracted. Papers are written. The planet is studied with a level of attention that almost no other puffy world receives. Why this much attention? Because the planet is unique. It is the largest confirmed exoplanet by radius. It has a clear, observable mass loss signal. It has a relatively bright host star, which makes it easier to study than fainter targets. It has a clean, aligned orbit, which makes its history easier to interpret. It is, in many ways, the best laboratory we have for studying atmospheric escape on a giant planet. The data being collected now will be used by scientists for decades. Even after HAT P67b is eventually engulfed, hundreds of millions of years from now, the data archived from this period will continue to be analyzed. Future generations of astronomers will look back at the records and draw new conclusions. They will refine models. They will test new theories. They will, in some sense, keep the planet alive in scientific memory long after it ceases to exist physically. There is something poignant about this. A planet that will not survive is being remembered in detail while it still exists. The light from HAT P67b that JWST captures today is light that left the system 1,000 years ago, traveling across space, finally reaching us in time to be saved in a digital file. By the time we see the light, the planet has been bleeding for another 1,000 years. The death, on cosmic timescales, is already further along than our most current data suggests. In the long run, what humans will know about HAT P67b will exceed what humans know about most planets in our own galaxy. The planet will be one of the most thoroughly documented worlds in the cosmic record. Its name will appear in textbooks. Its data will be reanalyzed for centuries. Its story, the story of a giant inflated by its dying star, will be told as a case study of how planets meet their ends. For now, the telescopes keep watching, the data keeps flowing, the story keeps unfolding, chapter by chapter, light curve by light curve, atom by atom, and every observation deepens the strangeness of the world at the heart of it all. For all the certainty around HAT P67b's size, its mass remains harder to pin down. The most recent measurement, from the NEED spectrograph in 2025, gives a mass of 0.45 Jupiter masses, plus or minus 0.15. That is a range from 0.3 to 0.6 Jupiter masses, a factor of 2 in possible values. For most planets, this kind of uncertainty would be considered acceptable. For HAT P67b, it matters more than usual because the planet's density depends on its mass in a sensitive way. A planet with the same radius but twice the mass would have twice the density. A planet with the same radius but half the mass would have half the density. The exact density determines how puffy the planet really is, which determines how the planet should evolve, which determines its expected fate. The error bars on the mass come from several sources. The host star's fast rotation is the biggest one. Even with modern techniques, the wobble of a fast-spinning star is hard to read with high precision. Stellar activity adds noise too. Pulsations and surface features can mimic the wobble of a planet, biasing the measurement in subtle ways. There are also systematic effects from the planet's own atmosphere. As the planet moves around the star, the gas trailing behind it can subtly affect the light from the host. Some of the wobble signal might come from the asymmetric distribution of escaping gas, rather than from the gravitational pull of the planet itself. Untangling these effects is part of why mass measurements take so long. The community has converged on a value, but it is a community-wide best guess rather than a precise number. Future observations, especially with more advanced instruments and better stellar activity modeling, may refine the mass to within a few percent. For now, the best we can say is that HAT P67b is roughly half the mass of Jupiter, give or take a sizable fraction. This is a humbling reminder that science from a distance is hard. Even with huge telescopes, spectrographs of exquisite precision, and observation campaigns spanning years, the basic question of how much a planet weighs can resist clean answers. The planet is more than 1,000 light-years away. Its host star is rotating fast and changing in real time. The signals are tangled with each other. The unknowns are real. One side effect of this uncertainty is that all the derived properties of HAT P67b carry the same uncertainty. The density is uncertain, the surface gravity is uncertain, the exact mass loss rate is uncertain, the exact lifetime of the atmosphere is uncertain, the exact engulfment timing is uncertain. Every prediction about the planet comes with a range of possible values. This is why the planet is described in slightly different ways across different research papers. One study might say the lifetime is 150 million years. Another might say 500 million. One might describe the density as cotton candy. Another might say marshmallow. The differences are not contradictions. They are different points within the same range of possibilities. For the purposes of telling the planet's story, the broad picture is clear. It is the largest confirmed exoplanet by radius. It is one of the lowest density planets known. It is losing atmosphere at a fast rate. It is going to be engulfed by its host star within the next few 100 million years. These statements are robust across all current measurements. Still, the uncertainty serves a function. It keeps astronomers humble. It keeps the field active. It encourages new observations, new techniques, and new instruments. Each generation of measurement narrows the range a little. Each refinement clarifies the planet's fate a little more. In the meantime, the planet continues to bleed. It does not care about error bars. It does not care about uncertainty. Whatever its exact mass, whatever its exact density, whatever the exact value of its lifetime, the planet is moving steadily toward its end. The countdown does not pause for science. There is a quiet character in this story that has been mentioned only briefly so far. The host star has a partner, not a planet, a second star. The companion is a red dwarf, a small cool star, roughly a third the mass of our Sunday. It orbits the main star at an enormous distance, roughly 3,400 astronomical units. To put that in perspective, Pluto orbits the Sun at about 40 astronomical units. The red dwarf companion is more than 80 times farther from HAT P67 than Pluto is from our Sunday. At that distance, the red dwarf is essentially a quiet observer. It does not significantly affect the orbit of HAT P67b. It does not interfere with the host star's evolution. It does not disturb the dynamics of the system. It simply orbits, slowly, taking tens of thousands of years to complete a single revolution around the main star. But the red dwarf is not unimportant. Its presence tells astronomers something about the system's history. Most stars are born in clusters or pairs, and many retain their stellar siblings for billions of years. HAT P67 and its red dwarf companion likely formed together from the same cloud of gas and dust. They have been orbiting each other since the system was young. Through all the disk migration of HAT P67b, all the drifting and inflating and atmosphere leaking, the red dwarf has been there, a constant, distant witness. In some star systems, a distant stellar companion can play a more active role through gravitational effects called Kozai-Ledoff oscillations. A faraway companion can pump up the eccentricity of inner planet orbits, sending those planets onto strange, looping paths. In some systems, this is the mechanism that sends planets crashing into their host stars or into wild, tilted orbits. For HAT P67b, the gentle alignment of the orbit suggests that the red dwarf has not played such a role. If it had, we would expect to see some kind of excitation in the inner planet's orbit. We do not. The system has been peaceful. The red dwarf has remained at its distant station, gravitationally quiet. There is also a subtle scientific advantage to having a distant companion. The red dwarf does not contaminate observations of the main star at the level of arcseconds, but it provides a context for the system's properties. Knowing the companion's mass and orbital separation helps astronomers refine the mass and properties of the main star. It is like having a tiny calibration source nearby. There is something quietly poetic about the picture. a dying main star, a bloated, leaking giant, a peaceful, distant red dwarf. Three objects bound together by gravity, evolving through cosmic time, each on its own trajectory. The main star will become a red giant, then a white dwarf, eventually fading into a stellar ember. The bloated planet will be engulfed long before that. The red dwarf will survive both of them. Long after HAT P67b has been absorbed into its host, and long after the main star has collapsed into a white dwarf, the red dwarf will still be there, slowly burning, slowly aging, quietly orbiting. Red dwarfs live for a very long time. Their lifetimes can stretch into the hundreds of billions of years, far beyond the current age of the universe. The companion to HAT P67 will likely outlive every other character in this story by orders of magnitude. It will see the main star become a corpse. It will see the planet become a memory. It will witness the slow cooling and final fading of the entire system. If any small planets orbit the red dwarf, they too will witness the end of HAT P67b. From their distant vantage, the main star and its bloated companion will appear as a single bright point of light, slowly evolving over millions of years. The death of the giant will be just a slight change in that point, a flicker, a dimming, a transition from one phase to another in the long life of a stellar pair. The galaxy is full of stories like this. Companion stars watching planets die, planets watching stars die, dust watching everything die. The universe writes its dramas across timescales no human will ever experience, and most of them play out without an audience. HAT P67b's drama, at least, will be witnessed by us. For a little while, what would it actually be like to be near HAT P67b? Not on it, because there is no real surface to stand on, but near it, perhaps in a hypothetical spacecraft, hovering at a safe distance, looking at the planet and its star. The first thing to strike the eye would be the host star. It would dominate the sky. From the planet's distance, the star would appear several dozen times larger than the sun does from Earth. Not a small, bright disk. A wall of fire, glowing fiercely white, taking up a significant fraction of the visible sky. The radiation pouring off it would be intense. Below the host star would hang the planet itself. From a distance of, say, a few planetary radii, HAT P67b would not look like a sphere. It would look like a hazy, glowing, slightly elongated cloud. The day side, facing the star, would shine bright, possibly with a faint reddish-orange tint from the heated atmosphere. The night side would still glow, more faintly, like a banked ember. The terminator, the line between day and night, would be a soft, fuzzy band, not the sharp boundary of a more solid world. Around the planet would extend the helium tail. To human eyes, helium itself is invisible, but the gas would refract starlight and scatter it slightly, possibly producing a faint, shimmering glow against the black of space. The leading tail would be larger and brighter. The trailing tail would be subtle. Both would stretch outward for many planetary radii, blending gradually into the background. Closer to the planet, the atmosphere itself would feel surreal. There would be no clear top. The gas would simply thin out gradually as you moved outward. Wisps of atmosphere would drift past the spacecraft as you got closer, slowly thickening. There would be no sharp boundary marking where the planet begins. Deeper in, the atmosphere would become more stirred up. Winds would howl, racing from dayside to nightside at supersonic speeds. Massive cloud structures, made of unusual high-temperature compounds, might form and dissipate over hours. The colors might shift, the pressure would build, the temperature would rise. If the spacecraft tried to descend further, it would be destroyed quickly. Even the most heat-resistant materials on Earth cannot survive in 3,000-degree environments for long. The vehicle would become superheated, then begin to vaporize, then disappear entirely into the atmosphere. The planet would absorb it, indifferent. On the day side, at any given moment, the air itself would be glowing. At those temperatures, Gas does not just sit there. It emits light in characteristic patterns. The atmosphere would shimmer with thermal radiation, the deep red and orange glow of an incandescent fluid. On the night side, the glow would be dimmer, but still present. Heat from the day side would constantly leak across to the night side, carried by those supersonic winds. The night side atmosphere would always be warmed, just a bit, just enough to glow. The whole experience, viewed from a distance, would resemble watching a slow, inflated comet, a planet in the act of bleeding, a world wrapped in its own dying breath. The image would be both magnificent and deeply unsettling. There is something fundamentally wrong about a planet so puffy, so close to its star, so visibly leaking. Earthly intuitions about what planets should look like break down completely. If a generation of cosmic explorers ever made this trip, they would witness an event that no Earth observer can fully see: the slow death of a giant, the transfer of mass from planet to star, gas atom by gas atom, the structure of a world that physics does not really endorse, held together by a temporary balance of forces that is shifting under their feet. They would also see a world that, by their time, might be much closer to its end than it is now. The further into the future the visit takes place, the more advanced the planet's destruction. Eventually, the planet would be a stretched, ribbon-like structure, half consumed by its swelling star. After that, just a glow. After that, nothing. For now, hundreds of millions of years before that final dissolution, the planet still hangs in the sky, visible only in light that has traveled 1,000 years to reach us. A reminder that the night sky is full of dramas humans have only just begun to read. It is tempting to look at a planet like HAT P67b and feel relieved that Earth is so different. Our planet is small, dense, rocky, in a comfortable orbit around a calm star. Our atmosphere is thin and stable. Our gravity is strong enough to hold onto our gases for billions of years. There is no violent, leaking, dying drama playing out around us. But the contrast is the lesson. Studying extreme planets like HAT P67b helps astronomers understand what makes a planet habitable and what makes a planet hostile. Every parameter that goes wrong on this dying giant is a parameter that has to go right on Earth. The host star has to be stable enough not to swell prematurely. The orbit has to be far enough not to overheat. The planet has to be massive enough to hold on to its atmosphere. The atmosphere has to be balanced enough to support liquid water. These conditions sound simple. The galaxy makes them rare. Most stars in the universe are not like our Sunday. Many are red dwarfs, small and cool, but prone to violent flares that can strip the atmospheres of nearby planets. Many are massive, hot, short-lived stars that age quickly and destroy their inner planets. Calm, sun-like stars in long, stable phases are a minority. Most planets in the universe are also not like Earth. Many are gas giants, like HAT P67b, too large and too gassy to support life as we know it. Many are tidally locked, like HAT P67b, with one face baked and one face frozen. Many orbit too close to their stars, baking and bleeding. Many orbit too far, frozen in eternal night. Earth sits in a narrow band of conditions, both in its star and in its own properties. We benefit from the calmness of our sun, the stability of our orbit, the right amount of atmospheric pressure, the protection of our magnetic field, the right combination of heat from the star and heat from our own interior. We benefit from a moon that stabilizes our axial tilt, from a Jupiter that catches incoming asteroids, from a position in the galaxy that is safe from supernovae. The miracle is not that we exist. The miracle is that all these conditions came together at once. Studying HAT P67b is, in a strange way, a celebration of Earth. It is a reminder that the universe is full of failed conditions, of planets that puffed up and bled away, of planets that were swallowed by aging stars, of planets that never had a chance. Earth is special not because it is normal, but because it is rare. There is also a darker lesson. The Sun, like all stars, will eventually evolve. In about 5 billion years, our star will begin to swell into a red giant. Mercury and Venus will be engulfed first. Earth's fate is uncertain. Some models suggest that as the Sun loses mass during its expansion, Earth's orbit will widen enough to escape engulfment. Others suggest that tidal forces will drag Earth inward and into the swelling Sunday. Either way, the long-term fate of our planet is not different in principle from that of HAT P67b, just slower. 5 billion years is much longer than 500 million, but the underlying physics is the same. Stars age. Planets that orbit close to aging stars are eventually consumed. Earth, in the very long view, is on a similar timeline to the bleeding giant. That thought puts human civilization into perspective. Whatever we build, whatever we record, whatever we discover, will eventually be erased by our own star. Maybe not for billions of years, but the same script that is being played out at HAT P67 in faster motion will be played out here too. The universe is patient. It absorbs everything in time. Studying HAT P67b is, in a quiet way, studying our own future, just on a different clock. Imagine yourself at the end of the planet's story. A few 100 million years from now, the host star has bloated into a deep red giant. Its surface, glowing dim and orange, has expanded outward to engulf the inner regions of the system. Where HAT P67b once orbited, there is no longer a planet. There is only the outer atmosphere of the dying star. The planet's last moments were violent. The atmosphere stripped completely. The deep interior, if there was a small core, fell inward through the swelling stellar atmosphere. Friction heated it to thousands of degrees. Tidal forces tore it into pieces. Each piece spiraled inward, glowing, vaporizing, dissolving. The star may have brightened briefly, a small flare lasting weeks or months, as the planet's energy was released into the stellar atmosphere. Some heavier elements, scraped from the planet's core, may have temporarily appeared in the star's outer layers, leaving a chemical signature for any distant observer. Then the star settled back into its dying expansion. The flare faded. The signature mixed into the broader stellar atmosphere. By that time, the planet is gone. There is no lingering remnant, no marker, no trace. The only thing that remains is the data stored back on Earth, or in whatever civilizations might exist by then. Spectrographs and light curves and papers, written by scientists who are themselves long dead. In those archives, HAT P67b lives forever. Its size is recorded. Its density is recorded. Its tail is recorded. Its alignment, its host star, its orbit, its leaking helium signal, all preserved in the digital memory of human civilization. A planet that no longer exists, perfectly captured in the moment when it still did. There is something strangely comforting about this. We tend to think of records as preserving things that are still here, photographs of living people, films of ongoing events. But records also preserve things that are gone. Old letters, recordings of voices that are no longer with us, footage of buildings that have been demolished. Each record is a small act of resistance against the erasure of time. For HAT P67b, the planet itself will be erased. The star will eat it. But the records of its existence will survive, at least until human civilization ends. The planet will live in light curves, in spectra, in research papers, in popular articles, in narrated science videos. People who are not yet born will study its data. They will know that, once, far across the galaxy, a planet bled into the dark. There is also a bigger picture to hold. The universe is full of planets like this. Some of them are forming right now, in distant disks of dust. Some are quietly orbiting stable stars in the long peaceful phase of their existence. Some are losing their atmospheres, like HAT P67b. Some are being engulfed. Some are already gone. This vast cycle has been going on for nearly 14 billion years. It will go on for trillions more. Stars will form, age, and die. Planets will form, drift, and dissolve. Atoms will move from cloud to disk to planet to star to nebula and back to cloud. The matter that makes up HAT-67b today, the hydrogen and helium streaming out in its long helium tail, was forged in the early universe and inside earlier stars. After the planet is engulfed, the same atoms will be released back into space when the host star sheds its outer layers. They will drift, mix, and one day form new stars and new planets. Nothing is truly lost in this picture, only transformed. HAT-P67b is, for now, a particular pattern of those atoms, a puffy, hot, leaking, doomed pattern. In a few 100 million years, the pattern will be gone. The atoms will move on, new patterns will form. The universe will continue, indifferent and patient, as it always has. For tonight, in the quiet of your room, the planet exists. It hangs in the sky of Hercules, 1100 light years away, glowing softly with its own heat, bleeding helium into the dark. It is the largest confirmed planet ever found by humanity. It is also one of the most fragile. It will not survive its own century. On the cosmic clock, sleep gently. The planet keeps bleeding. The star keeps swelling. The universe keeps its silence. And somewhere out there, in the vast dark, another giant is just beginning to inflate. Another story is just beginning. The night is full of slow dramas, written across timescales no one will ever see whole. Close your eyes. The light keeps traveling. We will be here when you wake.